In this chapter, we will consider benzene reactions. In the previous chapter, we've talked about the properties of benzene and how benzene is unique in terms of stability. Benzene is aromatic, and the reason why it's aromatic because it is made up of 6p orbitals that overlap above the ring and below the ring. That is going to create an electronic cloud in there that is going to make benzene electron rich. So in most of the cases, when benzene in here has no substituents on it, or if the substituents donate electrons to the benzene, these are electron donating group, benzene will be considered as a nucleophile. There are cases where you have benzene, and on the benzene, you will have an electron withdrawing group in there. Electron withdrawing groups, they take electrons away from the benzene. So when they take electrons away from the benzene, they are going to make benzene electron poor. So benzene in that case will behave as an electrophile instead of a nucleophile. So there are two cases for the benzene to consider and two different reactions to consider. An electrophilic aromatic substitution, where benzene acts as a nucleophile, and a nucleophilic aromatic substitution, where benzene acts as an electrophile. And it all depends on the substituents that are on the benzene. What are they? Are they electron donating groups, meaning that they give electrons to the benzene, making it electron rich? Or are they electron withdrawing group, meaning that they take electrons from the benzene and make it electron poor? Because benzene is aromatic and all the double bonds are conjugated, you cannot break one double bond without breaking the other. So let's say, for example, if I have a reaction of benzene and I want to add a bromine in there. We know that alkenes, they simply react with the bромines. Alkenes are not conjugated systems. So you can react an alkene with a bromine, and this is called a bromination reaction, where you form the cyclic brominium ion in there, and the bromine is going to add to the double bond. And this is called an addition reaction. Now with benzene, it's different because all of these double bonds over here, they are conjugated. So if you break one, then in this case, you will result with a non-aromatic compound. So if you have something like this, if this reaction happens and you break one double bond in there, you are going to go from an aromatic compound to a non-aromatic compound. This means that you are decreasing the stability of the product. Always, whenever you want to do a reaction, your product always needs to be stable. If your product is not stable, then the reaction cannot happen. So this means here that this reaction over here cannot happen as written, and I cannot break the double bond of the benzene. I can do that with isolated dienes. I can break each one alone, but when the double bonds are conjugated, I cannot break one without breaking the other. So as a conclusion, benzene does not undergo any addition reaction like alkenes. And just as a recap, addition reactions are when you break a pi bond and you form two new sigma bonds in there. This is called an addition reaction, and this is a property of alkenes in there or conjugated alkenes. This is different for the case of benzene because we said that benzene is a nucleophile, and if we consider the Lewis structure of the bromine in there and the direction of polarization, that bromine over here, it's not electrophilic enough in order to break the aromaticity of the benzene. This is why the reaction does not happen. So in order for benzene to undergo electrophilic aromatic substitution, you would need to form an electrophile. And that electrophile needs to be in desperate need of electrons so that it can react with the benzene and a product can happen. So let's start with the first type of benzene reactions. It is called an electrophilic aromatic substitution reaction. And in this type of reaction, if we look at the general reaction in there, you start with the benzene and you react the benzene with the electrophile. That electrophile needs to be in desperate need of electrons, and every time you will prepare the electrophile. The electrophile will end up replacing the hydrogen. This is why we call it a substitution reaction. The benzene starts being aromatic, and in the product, it ends being aromatic. So your product here is stable. All I did is I substituted the hydrogen with the electrophile. The reaction mechanism stays the same, except the steps that you need to use in order to form the electrophile. Those are going to vary. But the moment you make the electrophile, the reaction is going to go as in steps 2 and 3. So your arrow always starts from the nucleophile, from the benzene. Any of the double bonds of the benzene in there are going to open up and grab the electrophile. Remember that benzene is an electron source. So it's going to take the electrophile in there. So you're going to break the aromaticity of the benzene. On one carbon, you are going to end up adding the electrophile. You broke a pi bond in this case. So because you broke a pi bond, on one carbon, you're going to add the electrophile. And on the other carbon, since you broke the pi bond, that will end up having a plus charge. This is non-aromatic. It is not stable. However, it will be stabilized by resonance. So this is why you see in this step over here, in order to make this structure more stable, this is an intermediate. It's not yet the product. So in order to make that intermediate more stable, resonance structures happen. 3 resonance structures happen where the double bonds is moved along towards the plus charge just to stabilize the intermediate. So over here, this is going to be the intermediate in the reaction. Okay. In the second step, you take the carbocation that you formed with the addition of the electrophile. So you take just the first structure in there, and now you're going to react it with a base from the solution. Now, from where do we get that base? That base is always present whenever we are making the electrophile. The process generates a base. So that base, we're going to use it in order to regain the aromaticity of the ring. The role of the base is to come and take a hydrogen. Bases always take a hydrogen just to restore the aromaticity of the ring, and you're going to get your product. Let's start with the first reaction. The first reaction is halogenation, whether you are adding bromine or chlorine. With this reaction here, you would need a Lewis acid, because without the Lewis acid, we said that the reaction cannot happen. So you would need a Lewis acid, and the role of the Lewis acid is to make the bromine or the chlorine electrophilic enough so that the substitution will happen. Here I am substituting the hydrogen on the benzene with the halogen. There are 2 types of Lewis acids that we use, either iron chloride or iron bromide, depending on the halogen that you are starting with. It's better if you're starting with a chlorine halogen, then use iron chloride. If you're starting with a bromine, then use iron bromide Lewis acid. Just as a reminder, that Lewis acids, they do have an electron deficient site. So here, if I am looking at iron bromide, same thing for iron chloride in there. This iron over here, it does have an empty d orbital. Do the electronic configuration for the iron, you're going to see that it does have an empty d orbital, and that is going to make the iron electron deficient. So it will accept electrons in order to fill its d orbital. The mechanism is going to go as such, and you are responsible for these mechanisms. So the first step, you are going to make the electrophile. To make the electrophile, you start reacting the chlorine with the Lewis acid in there. So we said that iron is electron deficient, and because it's electron deficient, It can accept electrons. When I react iron with a chlorine will create a dipole, and that dipole, it's a temporary one. It's going to take electrons to this chlorine and make chlorine having more electrons than this other chlorine in there. So this is why one of the chlorines will be partial positive, the other one will be partial negative. It's the partial negative that it's going to act as a Lewis base because iron is Lewis acid. It's an electrophile. So I am going to give electrons from the chlorine to the iron and I'm going to create a complex in this case. Since I'm creating a complex, then this chlorine over here is going to lose electrons to make a bond between the chlorine and the iron. So the chlorine will be a positive charge, and iron will have enough electrons, so it will be a negative charge. This is going to be the complex in there, and that complex does have a leaving group, a good leaving group, and the good leaving group is all of this leaving group over here. So all of this leaving group is going to leave and you are going to end up getting your electrophile. So this is how you get the electrophile in there. So once you form your electrophile, the FeCl4 will be the conjugate base in the solution. And this is the base that we're going to use in order to restore the aromaticity of the benzene. So once you create the electrophile, then benzene is going to react with that electrophile by a nucleophile electrophile reaction. Double bond is going to open up, pick up the chlorine, break the aromaticity of the ring. So that is going to be non-aromatic. It will try to do resonance to stabilize the intermediate a bit. And then you are going to take one of the resonance structures in there, use the base that you formed throughout the process of making the electrophile. This is the FeCl4 in there. Use the base in order to take the hydrogen, form a double bond, restore the aromaticity of the ring. And that is going to be your final product in there. So all I did is I simply replaced the hydrogen on the benzene with a chlorine. This reaction could not happen if you did not have a Lewis acid in there. So the Lewis acid is a must in order to create the electrophile and form the conjugate base for the reaction to happen. Now that Lewis acid is considered to be a catalyst. So at the end, you will generate that Lewis acid back. So once you create that complex in there, the FeCl3 will be leaving a group and you're going to get HCl and FeCl3. This is the definition for a catalyst. The catalyst speeds up the reaction and at the end, you will generate it back. The reaction is carried the same if I am starting with a bromine instead of the chlorine. So here you go. Again, if I don't use a Lewis acid, the reaction will not work. So here I'm using an FeBr3. I can use an FeCl3, but it's better for the halogens to be compatible with each other, but I can also use an FeCl3 as well. So the Lewis acid here is a must for the reaction to happen. And the reaction is going to be carried by a simple substitution of this hydrogen over here with a bromine in there. And throughout the process, the bromine and the FeBr3 are going to react with each other in order to generate my electrophile, which is the Br plus in this case. So that is going to be my electrophile. You are responsible for the mechanism of the reaction, and always to start the mechanism, you always want to start by making the electrophile. So step one, you need to make the electrophile. And in order to make the electrophile, you react all the reagents together. This is a reactant in here. These two are the reagents. Start by adding them together or reacting them together in there. So I have my bromine. Bromine in this case is going to act from the Br negative to be my Lewis base. that is going to be my source of electrons, that is going to make a complex with the iron bromide. So the reaction is going to happen as such. The bromine is going to come and give electrons to the iron because we said that iron is electron deficient. And when it does, you are going to make a complex in this case. And the complex will result with the bromine losing electrons. So this bromine over here, I've used two of its electrons in order to make a bond with the iron. So in this case, the bromine is going to lose electrons and it's going to be a positive charge. And then the iron is going to be a negative charge because it gained electrons from the bromine. So that is going to be a negative charge in there. You can go ahead and put the lone pairs. Bromine here will have two lone pairs. Now, in this case, I made a very good leaving group. And the good leaving group here is everything, is the FeBr4 minus. So this is an excellent leaving group. It leaves on its own. And when it leaves, you are going to create your electrophile. So you're going to create the Br positive in this case. This is going to be my Br positive plus the FeBr4 negative. And that is going to be a conjugate base that you will use it whenever you need to take a hydrogen. So now for the second step, now for these steps over here, these are the reactions on the benzene. These are the aromatic substitution reactions. So the first step, I started by making the electrophile. You made the electrophile in here. So this is going to be your E plus. And every time you make the E plus, you're going to generate a conjugate base in the solution that you will use in the third step of the reaction. So now I'm starting with my benzene, and I'm going to react the benzene with the electrophile. This is the difference in there. I'm not reacting the benzene with Br2, I'm reacting the benzene with an electrophile. So this is going to be my nucleophile, this is going to be my electrophile. Now the reaction is going to happen from the nucleophile towards the electrophile in there. I will be breaking the aromaticity of the benzene. So I will end up getting a non-aromatic compound in there. So I'm going to have a bromine over here and I'm going to have a plus charge in there. Of course, I will have a hydrogen over here, and this hydrogen is the one that I am going to substitute. So this is the hydrogen in there. This is non-aromatic, but it is stabilized by resonance. So you can simply move those double bonds towards the plus charge to stabilize this non-aromatic intermediate. Then in the step number 3, I'm going to take that intermediate in there. Now in the mechanism, if I ask you, go ahead and write the stabilized intermediate structures, the resonance stabilized intermediate structures, please go ahead and draw them as well. So you have your bromine in there. This is the hydrogen. It's in this step that I would need a base, any base in the solution. And here in this case, I do have the FeBr4. This is the base. So I'm going to use the FeBr4 negative in there. And that base is going to come and take the hydrogen in there. And the reason why it takes this hydrogen, because this is going to be my sp3 hybrid hydrogen. So this is the only hydrogen that this base can come and take in there that can restore the aromaticity of the benzene, that can return the double bond back. So the base is going to come take the hydrogen, and those two electrons, I'm going to use them to make a pi bond over here and make the benzene aromatic again. And this is the whole idea. I started with an aromatic compound, and I need to end up with an aromatic compound. So here you go, and I'm going to end up getting my product in this case. Lone pairs belong in the base. Always draw the Lewis structure of that base to know where your lone pairs belong in that base. So over here, I do have an iron, and I have 4 bramines around it. So my lone pairs are belonging to the bramine and not the iron. So my nucleophile here is going to be any of those bramines in there. And this is where the reaction happens. This is where the lone pairs over here are going to come from the bramine and they're going to take the hydrogen. So pay attention to that. So in this case, when I'm regenerating that catalyst in there, I'm going to end up having an H that is going to react with the bramine and the rest of the complex in there. This is a Br, this is a bramine, and this is a bramine. The FeBr3 is going to leave, and I will be forming the HBr and regenerating the catalyst back.